Okay, so this is the Unit 2 review video for physics. Okay, so define the following terms and give an example of each. I'm not going to write out the answers from these. You can get these from the key. Okay, but distance is basically just the sum of where all that you traveled all added up. So there is no there is no negative. It's all positive. Just add it all up. Okay, and there is your distance. Okay, displacement is direction matters in this case. Okay, so if there's a positive values or there's negative values, those all matter. So you can't just make them all positive and add them all up. Okay, so displacement is technically your final position minus your initial position. So where did you end up versus where did you start? Distance doesn't care about all that crap. It just add everything up. Okay, in the middle, it's like mileage in your car. It just adds up. No matter which way you go, it just adds up. Displacement is where did you end versus where did you start? Okay, so if I left my house and I drove to Starbucks and that's 5 miles away, and then I drove back home and I said, hey, what's your distance? It would be 10 miles. You just add it all up. Now displacement would be, all right, where did I start versus where did I end? Well, I started at home and I ended at home. Then technically my displacement would be 0. Okay, so that's where direction actually matters. So that takes us into our next term is scalar and vector. So scalar is a number that does not have a direction, and immediately it affects distance. So distance is a scalar value. Okay, so if I just write out 60 meters, that is a scalar number because it's just a number. There is no direction. You have no idea which way it's going. It's just 60 meters. Now vector is something that has direction, and displacement is a vector. Okay, so as soon as I add on a direction, so let's just take 60 meters, but now I throw east on there. Now all of a sudden that's a direction. Okay, so that makes it a vector. Okay, so that's the big differences there. So number 2, a person walks 1.75 kilometers east, and then 2.5 kilometers west, and then 3.75 kilometers east. What is the distance and displacement? Okay, so distance, just throw out all the directions, just add up all the numbers. Okay, so there is no negative, so just add all those up, and you get a distance of 8 kilometers. Now, on my key, I will show a little bit more work on some of these problems. I'm just trying to save some time on here, so if you feel like I'm going too fast, okay, feel free to rewind it, okay, or if you want to try some problems out and then press play and see if it matches ours or matches mine, okay, that's another way you could use this video as well. Now, displacement, now all of a sudden, east and west matter. Okay, so displacement would be, displacement's that little triangle D. Distance is just the D by itself. Triangle D just means change. The triangle is change. So how much did you change your position? So now what I would do is I would do 1.75 minus 2.5, since that's going west now, and then add 3.75 since you're going back east. It does not matter which one you make positive or negative, as long as you make one of them positive or negative. So ultimately what we did is we ended up 3 kilometers. And remember, displacement has to have a direction, so that is east. Okay, so that would be how you kind of do that. Now, number 3, it says if you take the numbers from the previous problem and it took 6.5 hours to complete, calculate the speed and velocity. Speed is distance over time. Velocity is displacement over time. So you need to know when to use those and when not to. So distance would be 8 for speed, and then your time is 6.5 hours. So 8 divided by 6.5 hours, and you get 1.23 kilometers per hour. I don't need any directions on that. That's it. Now, velocity is displacement over time, so that is going to be 3 over 6.5. Divide those, and I get 0.46 kilometers per hour. Remember, this is a vector, so that means we ended up going east. Okay, so don't forget to leave off that east. What are the 3 types of motion on position versus time graph? First type, constant velocity forward, or I just abbreviate CVF. That just means, remember which we're about to do graphs here in just a second. Okay, if you're going the upward direction with a straight line, okay, that means you're going at a constant velocity. This would be like something like speeding up. Okay, like anytime you see a curved line, that's either speeding up or slowing down, but we're not gonna really worry about that just yet. Then you have constant negative motion or constant velocity backwards. Either way, it doesn't matter, backwards, negatives, however you want to say it, as long as you can understand the two. And then you have no motion. Okay, so that's a flat line. Okay, so that means we are not changing position on a position versus time graph, which we're going to do here in just a sec. What does solving slope tell us on a position versus time graph? Slope is velocity. So anytime I ask you to find velocity, find slope. 6, the steeper the slope on a position versus time graph means, well, think about skiing. If I have a slope that's this steep versus this steep, okay, the more the increase of steepness, or however you want to say that, increase steep means increase in velocity. What does a flat horizontal line on position versus time graph? Okay, so think of like in the hospital, you see a flat line on the EKG machine, they're not moving. Okay, so flat line would be no motion. All right, looking at this graph right here. Okay, so really pay attention to your units. Okay, X is always going to be time. Okay, that's not going to change. But on this test, you will have two different graphs. You'll have a position versus time graph, and you'll have a velocity versus time graph. Okay, so make sure you're reading that y-axis before you answer your questions, because you can get the rules mixed up. So for now, we're just focused on position versus time graph. Okay. Number 8, during what time intervals is there no motion? So that means when are there flat lines? So here, 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 and here. Okay, so those are your time intervals. Okay, so if I were writing those out, I would say 0 to 2, 7 to 12, 16 to 18, and 19 to 20. Now, during what time intervals is there constant positive motion? Okay, so let me switch colors here. Okay, constant positive motion would be here, because you're going up, and then here, right here, and then here. Okay, so there's 3 times you're going in constant positive motion. Okay, so I would say 5 to 7, 14 to 16, and 18 to 19. Okay, let me clear this up a little bit so we got some room there. Okay, so when is there constant negative motion? So when are we going down? So that's here and here. So only 2 instances does that happen. So that would be 2 to 5 and 12 to 14. Oops, 12 to 14. 11, during what time intervals is the object moving in a positive direction? Okay, so you're like, all right, well, didn't we just do that? Yes. I'm just kind of showing you different ways we could ask this. Okay, so key thing here is watch out for that constant. So constant just means we're not changing, the slope's not changing, it's not curved. Okay, and then when are you going into positive direction or positive motion? It's the same thing. Okay, so I just wanted to kind of let you see how it can be worded differently. So number 9 is basically the same answer for number 11. And then number 12, it says, when are you moving in a negative direction? The answer we have for number 10 is the exact same answer as well. What is the displacement from 0 to 7 seconds? So displacement, a lot of people get hung up on that. That is simply the change in position. So how much did you change in your y-axis? Okay, so from 0 to 7 seconds, let me clear this up. So from 0 to 7 seconds, so it's 0, I'm right here. Okay, so I have a position of 0. 7 seconds, I am right here. So how much did I change my position? Just I went up 2. That's it. Okay, so you could say 2 meters or a positive 2 meters. Okay, all that stuff in between doesn't matter. Okay, so distance, it would matter. So here in a second, we'll do that. Okay, but for now, for displacement, where did you end versus where did you start? So 14, what is displacement from 0 to 16 seconds? So 0, you're back at 0. 16 seconds, I am right here. Okay, so how much did I change? So I ended up at negative 2 meters. I just went down 2. So negative 2 meters. Now, number 15 was the total distance covered by the object. So now all the stuff in between matters. Okay, so let me clear these dots up. Okay, so first 2 seconds did nothing. Okay, that's a distance of 0, flat line. Then I went down 3 meters, so that's still a positive 3. So remember, distance can never be negative. We're just adding it all up. Then I went from negative 3 all the way up to positive 2, that is 5. Then flat line, so it didn't move. Then I went from 2 all the way down to negative 6, that is 8. Then I went from negative 6 up to negative 2, that is 4. Then a flat line, so 0. Then I went from negative 2 to 0, that's 2. And then flat line again, 0. So I would just literally add all that up, and then you should get an answer of 22 meters. Now it says number 16, what is the total speed of the object? This is when you need to look at your formula sheet. All right, speed is distance over time. Well, you just solved that in 15. So 22 was your distance. Time, if you look at the graph, the whole thing was 20 seconds. So there's your time. So 22 divided by 20, and you get a value of 1.1 meters per second. 17 was the velocity at 6 seconds. Okay, so let me clear this up again. All right, so at 6 seconds, we are right here. Now, different ways you could do this. You could do y2 minus y1, just take the endpoints. Like you could do the endpoints right here. Do y2 minus y1, so that would be 7, comma 2. And then right here, it'd be 5, comma negative 3. Do y2 minus y1, so 2 minus a negative 3. That becomes positive. Over 7 minus 5. And you could do that way. Or you could just do rise over run. You could even draw yourself a little triangle here. You went up 5 over 2, so 5 over 2. Okay, either way, doesn't matter to us as long as we get the same answer. Okay, and you should get 2.5 meters per second. So you just find slope. So velocity is a slope. So at 13 seconds, we are right here. Okay, so you could do the triangle here if you want to. You went down here and then over 2. So you went down from 2 to negative 6, that's 8 over 2, so 8 over 2, so negative 8 over 2. So in this case, sorry, you went down 8. So negative 8 over 2, and that gives you negative 4 meters per second. What is the velocity at 16 seconds? So at 16 seconds, we are right here. That is a flat line, so that means you have a velocity of 0. Okay, so that's 0 meters per second. Average velocity from 12 to 19 seconds. So velocity is slope. Well, what if we don't have the slope of a line that's connecting the 2 points? Okay, so let me clear this up. So we've got some room to do this. So what was our time again? It was 12 to 19 seconds. So at 12 seconds, I am right here. At 19 seconds, I am right here. Okay, so you got a lot of stuff in between. You could just connect the 2 points and find the slope of the line. Okay, so you could draw your little triangle right here. So you went down negative 2. Okay, and you went over, so you went from 12 all the way to 19, so that is 7. Okay, so this would be negative 0.29, so negative 0.29 meters per second. Okay, that's it. Number 21, write the units for the following. I'm just going to give you the most common ones you'll see. So distance is usually meters or kilometers. Okay, time is usually seconds or hours. Okay, velocity is meters per second or kilometers per hour. Okay, and then acceleration, we don't worry about the kilometer stuff, so it's always going to be meters per second squared. Okay, so I will say one of the bigger missed units is that one. Okay, you've got to understand that whole meters per second squared is acceleration. All right, number 22, a motorcycle travels 55 meters in 8 seconds. Okay, so that's a distance, and that's a time. Then travels 90 meters in 10 seconds. Well, that's another distance, and that's another time. And then 75 meters in 7 seconds. That is distance, and that's another time. Calculate average velocity. V average is total displacement over total time. Okay, so if I have displacements and I have times, this is a simple problem. We're just going to add up the whole top. So 55 plus 90 plus 75 over your total time. So 8 plus 10 plus 7. Okay, and what you're going to do is just add all those up on top, add everything up on bottom, divide, and you get 8.8 meters per second. That's it. Okay, now that's a simple one. That is a one-step problem. Okay, and then you're done. Now in 23 and 24, I'm showing you how there can be a difference, like or when it's not just a one step. You actually need to find something you're missing. Okay, because on our last quiz, this is probably one of our bigger missed problems. Number 23, a runner jogs 3 meters per second for 25 seconds. So what I'm going to do is I'm going to clear this up so I can kind of label stuff. So if you need to go back and rewind or check the key, you can. Jogs at 3 meters per second. That is a velocity. So we're going to say that's velocity 1. For 25 seconds, that is time 1. Then speeds up to 4 meters per second. That's V2. For 40 seconds, that's T2. Then slows down to 2 meters per second. That's V3. And then 30 seconds, that's T3. Calculate average velocity. So I've seen students do these things wrong in two ways. One, they just add up all the velocities and divide by the number of velocities. So 3 plus 4 plus 2, divide by 3. While technically that is finding average, that is not how you find average velocity because you're changing your speeds constantly. Or what I'll see is they just add up all the velocities on top, add up all the times on bottom, and then divide. Okay, remember the equation is total displacement over total time. Do I have displacements? I don't have them at all. So I need those before I can even do it. We're just going to do that by doing V equals D over T. Okay, so my velocity is 3. My distance, I don't know. My displacement, I don't know. Okay, and then time is 25. Okay, so all I got to do is multiply both sides by 25. So that means D1 would be 75 meters. You're just going to do that for everything. Okay, so you would do 4 equals D over 40. So 4 times 40, that means D2 equals 160 meters. Then you do it again. So V equals D over T. So 2 equals D over 30. Multiply those two. So D3 equals 60. Now I have my distances. Now I have my times. Now I can add all those up. So 75 plus 160 plus 60 over 25 plus 40 plus 30. Okay, then just solve that and you get 3.11 meters per second. Okay. Number 24, car travels at 25 kilometers per hour. That's V1. For 500 kilometers, that's D1 now. And then speeds up to 45 kilometers per hour, that's V2. And then for 750 kilometers, that's D2. So what I did is I gave you the other type is what happens when I give you distances now and we don't have times. We're just going to do the same thing. V equals D over T. So 25 equals D, which is 500, over time. Now, I will say be careful the math here. Do not just multiply both sides by 500. That would be the case if 500 is on bottom, but it's not. Remember, you can do this little trick right here. Okay, you can switch those two anytime a variable is on bottom. So 500 divided by 25. And that gives you a T1 of 20 hours. Then you're going to do the same thing for 45 kilometers per hour. So 45 equals 750 divided by T2. So 750 divided by 45, and that gives me a time 2 of 16.67 hours. Now, do I have distances? Yes. Do I have times? Yes. So now I can do the whole V average equation. So I would do 500 plus 750, and then do time on bottom, so 20 plus 16.67. Sometimes I forget how to write. Okay, then you get 34.09 kilometers per hour. 25, a car travels at a velocity of 15 meters per second and speeds up to 45 meters per second in 12 seconds. Okay, so I have a velocity. I do have a velocity, but you notice I have two of them now. Okay, so I started off at 15 meters per second, so that is your V initial, okay, where you initially started. You sped up to 45 meters per second, that's V final. In 12 seconds, that's time. What is the acceleration? There's your question mark. Now, two ways you can do this. You could use the acceleration equation, which is change in V over T, which is just V final minus V initial over time. Or you could set up the whole 5 equations, dA, VF, VI, and T, and use the 5 kinematic equations. Either one works, okay, so it does not matter which one you pick. Okay, so I think on the next problem I'll show you both ways, but this one I just used the first equation. So VF is 45 minus VI, which is 15. Okay, over my time, which is 12. Okay, and I get 2.5 meters per second squared. That's it. Okay. Number 26, a runner accelerates from 1.5 meters per second, so that's VI because it said from, at a rate, let me clear this up a little bit, or in this case, let me clear it up, and then I'll switch up colors just to change things up. Okay, so a runner accelerates from 1.5 meters per second, that's VI, at a rate of 5.5 meters per second squared. So be careful with this. I said accelerates from 1.5 meters per second. That does not mean that's my acceleration rate. Okay, this 5 meters per second squared is my acceleration. and it does it in 7 seconds, so that's time. Okay, what is the final velocity? So you're looking for VF. So I'm going to do this both ways. So I'm going to do the equation I just used, A equals VF minus VI over T. Well, technically I know A, so I can just go plug that in. A is 5, equals VF, I don't know, minus VI, which is 1.5, over T, which is 7. So what I would do is multiply both sides by 7, so 7 times 5 is 35. Add 1.5 to the other side, and you get a VF of 36.5 meters per second. Or you could set up the whole, in my class we call it Daffy T, so DAVF What I would do is I'd plug in, so VI is 1.5, A is 5, T is 7, and we're looking for VF. That's your question mark. Okay, so whichever one they don't mention, we just draw a line through. Okay, and when you're looking at your formula sheet, okay, we give you those 5 equations, and they're in this order specifically. So if you use the equation that they don't care about, so if they did not mention D or ask for it, you're going to use the first equation. You don't use the equation you're using a question mark on, because if you look at that equation, you're not going to find what you're looking for in there. Okay, so if you try to pick out an equation that doesn't even have the variable in it, it's not going to work from the get-go. So we're going to use equation number 1, so VF equals VI plus AT. So VF we don't know, VI is 1.5 plus A, which is 5, T, which is 7, and then you just solve for that, and you get 36.5 meters per second. Either way works, doesn't matter. Okay, an airplane accelerates down runway at 3.20 meters per second squared, that is A, for 32.8 seconds, that is time, until it lifts off the ground. What is the distance traveled? Now, if you're trying to set up your whole D, A, VF, VI, T, okay, so time is 32.8, A is 3.20, what is the distance traveled? So that's my question mark. You're like, all right, well, I'm missing something here. Okay, you've got to read some of these problems. Sometimes you will have context clues. When you're talking about a runway, a plane, usually it starts from what? It starts from rest and then takes off. So your VI would be 0 in this case. So you've got to be able to read some of these problems, because we may not give you everything, but it's implied in the problem. So that means VF did not matter. So we're going to use equation number 3, which is displacement equals VIT plus 1/2 AT squared. Okay, so just plug in. So D we don't know. VI is 0. So here's the good news. Anytime VI is 0, just cross off that whole VIT, because 0 times T is 0. So I've seen students that will leave that T in, and then they're trying to solve an algebra nightmare because they've got T and T squared in the same problem. Okay, so 0 times T is 0, so that just goes away. So 1/2 A, which is 3.20, and T is 32.8, and that is squared. Now, only time is squared. Do not square that whole thing. It is just time that's squared. Okay, so be careful with that. That can give you a really big number, and all of a sudden you're looking at a multiple choice question, you're like, oh crap. So you're going to get 1,721.34 meters. That's your answer. The car starts from rest, so there goes VI right there. Accelerates uniformly. Don't get hung up on this. Uniformly just means it's not changing. Okay, so if you wear a uniform at private school, everybody looks the same. Okay, so it just means it's not changing. If it was changing, this problem would be a lot harder. Okay, over a time of 5.21 seconds, that's your time. For a distance of 110 meters, that's D. Determine the acceleration of the car, that's your question mark. So we're just going to set up our Daffy T. So VI is 0. Okay, time is 5.21. Okay, D is 110. Acceleration is your question mark. VF didn't matter again. So equation number 3. So D equals, so 110 equals VIT. Well, VI is 0 again, so that gets to go away. So that's nice. So equals 1/2 A, which we don't know. T is 5.21. And 5.21 is squared. So what I would do is I'd take 110 divided by 1/2. Be careful. Do not divide by 2. That is not the same thing. So 110 divided by 1/2 is 220. And then divide that by 5.21 squared. Okay. If you feel like if math is a struggle for you, I would definitely do as many steps as I could. I've seen a lot of students that try to do this all in one swoop on a calculator, and then they just get confused or they get the wrong answer because their calculator is doing the wrong thing. Okay, baby steps. Just do one step at a time. So we get an acceleration of 8.11 meters per second squared. Number 29. An object free falls for 2.06 seconds. Now, we're talking about free fall here, so I'm about to explain here in a second. That's time. What will its final velocity be? So VF is a question mark. And how far will it fall? That's D equals question mark. So, free fall. Anytime you throw something or drop something, we're still going to set up our whole Daffy T. Now, when you're falling or throwing something, what's acting on it? Gravity. A is going to be negative 9.8 meters per second squared. It won't change. Okay, and it's always negative because which way is it pulling? Down. Okay, now, also a thing to know about dropping. Anytime something free falls, it originally wasn't falling, and then it was. So what was its initial velocity if it wasn't falling? So VI would be 0. Okay, so those are two implied things as soon as we start mentioning free fall. Okay, because if you're looking at this problem like, man, you only gave me time. I don't know what to do with this. Well, I said free falls. Okay, so that means you have to know that gravity is a factor, and it started off with a velocity of 0. Now I can plug in time. Now all of a sudden this is looking a lot more doable. So VF is my question mark. So we're just going to do this one step at a time. Don't try to solve both at the same time. Make your life a nightmare. Okay, so distance did not matter. So we're going to use equation number 1. So VF equals VI plus AT. So VF we don't know. VI is 0 plus A, which is negative 9.8. Time is 2.6. And we get a final velocity of negative 25.48 meters per second. So that's okay, it's negative because it's going down. Now, we're looking for how far did it fall, so we're going to set up Daffy T again. Now, here's what I like to do, is I like to stick with what I know that did not change, that was from the original problem. Technically, now that you know now that you know VF, could you plug it in? Yes. Okay, but two things. One, you have to bank on that being correct. And then two, you're going to have to mark off something else to figure out which equation to use. You can totally do it this way, but as long as you find an equation that has distance in it, you can use that, and as long as you have all the other variables, go for it. But I like to stick with what I know. I know that time didn't change, so 2.60. VI was 0. A is negative 9.8. So I like to stick with what I know, just in case I messed up. Then how far will it travel? So distance is my question mark. That means VF did not matter, so we're going to use equation number 3. So D equals VIT, so VI is 0, so there goes that again. So equals 1/2 A, which is negative 9.8. T is 2.6, and that is squared. So just solve for that, and you get 79.78 meters. Number 30, a race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. What's the acceleration of the car, and what's the distance traveled? So let's set up Daffy T again. Okay, so you started off at 18.5, so there's your initial velocity. Okay, you went up to 46.1 meters per second, so that's your final. And you have 2.47 seconds. And you said, what is A? Now, be careful with this. Some people get hung up. As soon as we start mentioning free fall or throwing something, they just start putting negative 9.8 in every single problem. If I'm not throwing this car or dropping the car, gravity is not a factor. Now, is gravity technically still holding the car against the earth? Yes. But is it affecting its motion? No. Okay, so don't use gravity unless it's being thrown or dropped. Okay, so A is my question mark. That means D did not matter. So VF equals VI plus AT, so 46.1 equals 18.5 plus A times T, which is 2.47. Be careful with your algebra here. So subtract 18.5 from both sides and then divide by 2.47. And you get 11.17 meters per second squared. Okay, so let's look at distance now. So let's do dA, VF, VI, and T again. I'm going to use the same numbers, 2.47 for time, 18.5 for VI, 46.1 for VF. I'm going to mark off A now, even though I already know it. And then question mark is D. So we're going to use equation number 2. So that is D equals VIT. I'm sorry, nope, wrong equation. Got used to using that. Equals VI plus VF over 2 times T. So that's equation number 2. That's what it looks like. So D equals 18.5 plus 46.1 divided by 2 times 2.47. Okay, so again, take this in steps. You're going to get a distance of 79.78 meters. Oops. Well, if you're wondering, why did 29 have a wrong distance? Okay, you're like, well, I'm going to send him an email. Okay, that's because I was looking at the wrong problem on the key. So if back on 29, if you get a distance, let's go ahead and mark that out. That was a mistake that I made. If you got a distance of negative 33.12 meters, that would be correct. So I'm not always correct. So I just looked in the wrong spot. I was like, well, that looks oddly familiar. Okay, so the distance for number 29 was negative 33.12 meters. And the distance or height for the next problem is 79.78 meters. Oops, my bad. 31. A feather is dropped on the moon from a height of 1.40 meters. The acceleration of the gravity of the moon is 1.67 meters per second squared. How long will it take for the feather to fall? So dA, VF, VI, and T. So we are dropping something, so VI is still 0, but we're not dealing with gravity anymore from Earth. We're dealing with gravity from the moon, so that's negative 1.67 now. Even though I told you it's positive, so this is where you got to know, well, it's going down, right? Okay, so negative 1.67. Okay, now it falls 1.4 meters. Okay, so you're going down 1.4 meters. So it'll be negative 1.4 meters. Now, here's where you'll kind of run into some issues sometimes. Okay, is if you miss a sign. So A, we'll usually see it if someone solves for time and they get a negative time. Can you have negative time? No. That means you had somewhere there was something that should have been negative and you had it as positive, or vice versa. Or what happens when you're solving your equation, you got to take a square root of a negative, and all of a sudden you're getting a calculator symbol that says error. Okay, that is because you messed up on a sign somewhere. Okay, you cannot take the square root of negative. So go back and look. All right, look at my directions. Which way are things going? Anything going down, just go ahead and make it negative. So if you're falling, negative distance, negative acceleration, negative velocity. Okay, so that just makes it a lot easier that way. So how long will it take for the feather to fall? So that means T is your question mark. So that means VF did not matter. So equation number 3 again. So D is negative 1.4 equals VIT. So VIT is gone. So equals 1/2 A, which is negative 1.67, and then T squared. So this is what I mean by if you didn't have that negatives in there, okay, that's where it would have messed up your square root. Now, if you would have marked both them positive, would have changed it? No. Okay, but sometimes you will run into snags where that happens. Okay, so just be careful with signs. So what I would do is I would combine the 1/2 and negative 1.67 to get that as a number, and then divide both sides by that. If you do that, you're going to get 1.68 equals T squared, and then now square root both sides, and you get a time of 1.30 seconds. 32, a kangaroo is capable of jumping onto a height of 2.62 meters. Calculate the takeoff velocity of the kangaroo. Again, I only gave you one value. But we're talking about jumping up in the air, so it's kind of like throwing something, so gravity is a factor. So gravity is what's pulling the kangaroo back down, so A is negative 9.8. Now, you got to be careful on this. Anytime we drop something, VI is 0, but if the kangaroo's jumping, if the VI was 0, it wouldn't go anywhere. It'd just be sitting there. Okay, so VI is what we're actually looking for. We're looking for the takeoff velocity. Okay, now, when you throw something up in the air or the kangaroo jumps to its max height, what is your velocity at the max height? 0. Because when you reach the top of your jump, you have to stop and then you come back down. So VF is now 0. And then my distance was 2.62 meters. So that means T did not matter. So equation number 5, so VF squared equals VI squared plus 2AD. So VF is 0. 0 squared is 0 equals VI squared, which we don't know. We're going to leave that as VI squared. Plus 2 times negative 9.8 times distance, 2.62. Solve all that, move it to the other side. It becomes positive. That becomes 51.35 equals VI squared. So take the square root of both sides, and you get VI is going to come out to be 7.17 meters per second. Okay, number 33, what does slope tell us on a velocity versus time graph? Now we're hitting that second graph. This is where we're going to see a lot of confusion, okay, is when you start blending the two rules. Okay, so slow it down, look at each graph, check the y-axis to see which one are you dealing with. Because on a velocity versus time graph, what you're doing is you're changing velocity now, and if you're changing velocity, you're accelerating. So slope equals acceleration now, which we're about to do a whole graph on that. On a velocity versus time graph, when is the object traveling in a positive direction? Anytime you're above the x-axis. That is when you're going in the forward direction. Anytime you're below the x-axis, you're going in a negative direction. Okay, that is below the x-axis. So anytime I ask you when are you going backwards or in the negative direction, anytime you're below. 35, when is the only time an object is not moving on a velocity versus time graph? That is when it touches the x-axis. That is when your velocity equals 0, which I'm about to make all this make sense. All right, here's my v versus t graph. I know it is because if I look at my units, I have velocity, v versus t, so my time is right here. Make sure you're reading that on the test, because if you're trying to do position versus time graph rules on a v versus t graph, you're going to get answers wrong. Okay, so in my class, I like to ask two things. One, is it going forward or backward? Okay, so anytime you are above the x-axis, that means you're going in the positive direction. That means you're going forward. So all that is going forward. Anytime you're below the x-axis, that means you're going backwards. You're going in the negative direction. That means all of this is going backwards. Now, the second question I like to ask is, well, let me clear this up first, and then I'll do it. Are you going towards the zero line or away from it? So I'm going to highlight it in red. You've got to really pay attention to this zero line right here. That will tell you a lot. Okay, that tells you, A, if you're not moving, because if you're touching it, that means you're not moving. And then are you going away from it or are you going towards it? If you're going away from it, you're speeding up. If you're going towards it, you're going 0. I'm sorry. If you're going towards it, you're slowing down. So I'll do a real quick example. So when is the object speeding up? Anytime you're going away from 0, so like here, you're going away from 0, that's speeding up. That's speeding up in the forward direction. Then you hit a flat line. That means doesn't mean I'm not moving. Be careful of that. I'll see people say, well, you're not moving from 3 to 8 seconds. No. Do you have a velocity of 0? No. You have a velocity of 1.5. That just means you're constantly going 1.5. Now, big thing that people will miss is this line right here. As soon as it starts going down, they're like, all right, now I'm going backwards. No. If you're still above the x-axis, you're still going forward. It just means you're slowing down. Your velocity is just going towards 0. Please do not mistake that, because on a position versus time graph, yes, you'd be correct. If this was a p versus t graph, then yes, you'd be going backwards. But on a v versus t graph, you have a different set of rules. Then we stop right here from 11 to 13 seconds because you have a velocity of 0. It's a flat line, and you're just staying at 0. So flat lines don't always necessarily mean you're going 0, but if you're touching the 0 line, yeah, you're going 0. Then we're speeding up. We're going away from 0, but now you're below the x-axis, so you're going backwards. Then you have a flat line, so that means you're constantly going -2. And then now you're going back towards 0 again, so that means you're slowing down. You're still going backwards. Just because you're pointing up doesn't mean you're going forwards. You're just going back towards 0, just going backwards. You're slowing down. Okay, so now I'm sure we just answered a lot of questions that's about to ask, so it doesn't hurt to kind of explain it first, and then y'all can kind of see the questions as soon as I can figure out how to erase all this stuff. Okay. What time rule is the object speeding up? So when am I going away from 0? Here and here. That's the only times. Okay, so I would say, if I was writing out intervals, I would say 0 to 3 and then 13 to 14. What time is the object slowing down? So when are you going towards 0? So here and then here. Okay, so I didn't say forward or backwards. I just meant when are you slowing down? So it could be either directions. Okay, so I would say 8 to 11 and 19 to 20. Okay, so let's clear up this graph again so we can answer some more. Does the object ever come to a stop? If so, when? Yes, anytime you touch that 0 line. So that means right here you stopped, and again right here. Okay, so I would say you stopped from 11 to 13 seconds, and then you stopped again at 20. So what time intervals is the object not accelerating? That means constant velocity. When are you not accelerating? Okay, when are you not changing your velocity? Let me switch colors. That's when I'm looking for flat lines. Okay, I am not changing my velocity there. Technically, I'm not changing my velocity here. Okay, just because you're not moving, yeah, are you not accelerating? Correct. Okay, so would I accept that one? Yeah. And then here. Okay, so I would say, when are we not accelerating? That would be 3 to 8, 11 to 13, and 14 to 19. Okay, what is the maximum velocity attained and when did it occur? So let me clear it up again. So maximum velocity, all you gotta do is just look at the left side. Okay, look at the y-axis. That's all you gotta do. When are we going the fastest? Okay, so I'm gonna look at both top and bottom and see what their values are. Well, if I look right here, my max velocity is 1.5. That's as high as I got going forward. And if I look here, this is as high, this is as low as I got going backwards. It's -2. So when was I going the fastest? When I was going -2. Okay, so I would say, when did that happen? Well, what is my maximum velocity? It'd be -2 meters per second. And when did it happen? That would be 14 to 19 seconds. Did the object ever change direction? If so, when? Okay, so as soon as you go from above the x-axis to below the x-axis, that's when you change direction. And it happens right here. Okay, so it doesn't really happen from 11 to 13. You just stop. Doesn't mean you're going backwards yet. So I wouldn't say 11 to 13 seconds. I would just say it happened at 13 seconds. Okay, because that is when you dipped down into the bottom or the negative part of the y-axis. Okay, 42. What time intervals does the object travel in the positive direction? Okay, let me clear this up. So be careful with this. It does not mean just look for lines that are going up. Okay, you just want to look for when are you above the x-axis. Don't make this harder than it is. That is it right there. So you would just say 0 to 11 seconds. When is the object going in the negative direction? Anytime you're below. So all that. Okay, so that'd be 13 to 20 seconds. Number 44, what is the change in velocity from 3 to 16 seconds? Okay, so this is almost like doing displacement on that last graph. We're just looking at what is our change in y. So 3 to 16 seconds. So 3 would be right here. And at 16 seconds, I'm right here. So how much did I change my velocity? Well, I was at 1.5 here. And now I'm at -2 down here. So what's the gap? So it went down by how many? So it went down -3.5 meters per second. What is the acceleration at 9 seconds? So remember, acceleration is slope. So at 9 seconds, you're right here. So you could do the whole y2 minus y1 over x2 minus x1, or just draw me a triangle. Okay, just do your rise over run for the whole thing. Okay, so you went down 1.5, so -1.5, and you went over 3. So you would just do -1.5, rise over run, over 3, and you get -0.5 meters per second squared. Number 46, what is the acceleration at 19.5 seconds? So at 19.5 seconds, we're right here. So you could do the whole y2 minus y1, or you could just do rise over run, just do your little triangle. You went over 1. Well, let me clear this up and give it some room. Okay, you went over 1, and you went up 2. Be careful. So really be careful of your segments here. If you just go off by squares and all of a sudden you're like, well, I went up 4 squares, so 4 divided by 1 is 4. No, each square is 0.5. So you got to really pay attention to your increments on the graph. Okay, so 2 divided by 1 is 2 meters per second squared. Then the last one, 47, was the average acceleration from 3 to 14 seconds. Let me clear this up and then we'll knock out this last one. So average acceleration, just like we did average velocity on the position versus time graph, just connect the 2 points. So from 3 to 14 seconds. So 3 is right here, 14 seconds is right here. So you can draw a big triangle if you want, or you can just connect the 2 points and find slope. I'm going to do it that way. So this would be 3, 1.5. And then this would be 14, -2. So y2 minus y1, so -2 minus 1.5, over x2 minus x1, so 14 minus 3. And then you just solve. Okay, and you get negative 0.32 meters per second squared. That's it.